Hi, everybody. It's a great pleasure for me to welcome you in the Flug Auditorium of our Aspen Center for Physics. My name is Vicky Kalogiera. I'm a professor in physics and astronomy at Northwestern University, but I have been also a member of this center for many, many years. I've been coming here for almost 20 years, almost every summer. And now I also have the honor of serving as one of the trustees of the center. Now, before we get to the topic of tonight's lecture, I want to give you, for those of you who may not know, I want to let you know a little bit about what this Center for Physics is. It's actually, in a short sentence, it's actually summer camp for physicists. So we love it here. That's why we keep coming back. Every summer, over a period of about 16 weeks, about 500 scientists from all over the world, having gone through an annual highly competitive selection and application process, come here. Each physicist comes for 2 to 3 weeks, and we attend a series of different programs. But most importantly, we come here to, in some way, isolate ourselves and work on current research problems, interact with colleagues that we don't see that often, debate with them, discuss new ideas and new questions, formulate new projects, and go away rejuvenated, having made progress in our research. The big advantage for the Aspen Center for Physics is that basically it allows us to escape from our everyday, day-to-day obligations at our host institutions. We come here and we really get the time to sit back and really think. And that's very valuable these days. No interruptions, just talking and thinking about research for our whole stay. And of course, we get to be here in this amazingly beautiful natural physical environment, which you know and experience even better than we do. So we also enjoy very much to interact with our local community with evenings like this, so please keep coming in. There are multiple lectures every few weeks. In fact, before I introduce our speaker tonight, I'll remind you that the next lecture is scheduled for July 22nd. No, I'm sorry. I thought I was going to get it wrong. 21st, same time, and the topic is going to be how we bring together string theory and quantum physics. But today, you're going to hear about potentially what may turn out to be the most important discovery of this century, at least in physics, but maybe all of science. The discovery of binary black holes colliding with one another, and our ability to detect a new type of waves that they are emitting, gravitational waves, that Einstein predicted about 100 years ago. And only a century later, we have been able to actually detect them, and in this way, open up a completely new way of studying the universe. Now, I won't tell you all about it, because our speaker will tell you all about it, and it's a great pleasure to introduce Ilya Mandel today. Ilya did his undergraduate studies and also got a master's in computer science at Stanford University, physics undergraduate, master's in computer science. And then he moved to Caltech, where he worked with Kip Thorne for his Ph.D. studies. Kip Thorne of the black holes and interstellar movie fame, if you remember the name. In 2007, upon his graduation, I was fortunate enough to attract him to Northwestern, where he joined my LIGO group. LIGO is the instrument that detected the gravitational waves. And he joined my group as a postdoctoral researcher, became an NSF National Science Foundation fellow, and after a short year at MIT, he joined the faculty at Birmingham, University of Birmingham in 2011, where he went up the academic ladder very quickly, and now he's a professor of theoretical astrophysics. Now, Ilya has worked over the years on a number of different topics related to black holes in different environments in the universe, and also has worked on trying to understand how these things form, how they emit their gravitational waves, but also has worked on actually analyzing data that come from the LIGO detector. He and I have had this great pleasure this past year to experience up front this discovery that at some level we didn't expect. And it has been my great pleasure over now almost 10 years to work with Ilya. He's one of the, I'm going to embarrass you of course now. He's one of the truly sharpest, quickest physicists I've ever had the opportunity to interact with. And at the same time, he's a pleasure to work with. I certainly learned a lot from him, and hopefully he learned one or two things from Northwestern and my group as well. So at this point, I'll ask Ilya to step up and tell us all about chirps from black holes.
I have to be careful not to bring this too close, otherwise, given my voice, you might all go deaf. So, good afternoon, everybody. Vicky, thank you very much for the very kind introduction and for not embarrassing me too much. Also, thank you very much to the Aspen Center for Physics, and I don't know if Patty is here, but thanks to all of the people here for organizing these events. And most importantly, thanks to all of you for coming here to hear about some of the exciting work that we get to do at the center as well as outside of it. So as you can see from the title on the slide over here, I will try to tell you a little bit about singing binaries, merging pairs of black holes that, as you can see on this image, are emitting gravitational waves. And I'll explain what those words mean over the course of the talk. And I promise that we will actually get to sing a little bit during the talk, and maybe we'll even get to talk about rock stars and dinosaurs. I've tried to sneak in as many random things as I could, but I'm getting a little bit ahead of myself, so let's start slowly. So we start slowly, and of course, people long ago have been very excited about the night sky, have been fascinated by the stars, and so we're looking up in the heavens above and getting, well, as you can see, extremely happy about this. Now, at some point, people realized, Galileo in particular, that one could look at the skies much better with a bit of technology. And so along came telescopes, and later on computers, and later on graduate students to analyze the data coming down via the telescopes and the computers, which is really good for theorists like me, because to be completely honest with you, I'm not sure I would know which end of the telescope to look through. So this chain is fantastic. Okay, so that's the standard picture of looking at light or electromagnetic radiation, as physicists call it, which is everything from the optical to the X-ray to the radio waves, electrons fluctuating around and emitting electromagnetic radiation. Okay, now that's electromagnetism. Now there's, of course, another important force that's part of this, and that force is gravity. So, as we all know, it's very simple to discover gravity. All you have to do is sit on a nice day under an apple tree, wait for a suitably sized and shaped apple to hit you on the head, and if your name is Isaac Newton, I'm not sure if it works for everybody else, but if your name is Isaac Newton, you realize there's a law of universal gravitation, that all objects are attracted to each other with a force that is proportional to their masses and inversely proportional to the square of the distance between them. And this force operates between all objects in the universe, whether it's apples and the Earth, or whether it's planets or black holes. And it's sort of instantaneous. It automatically attracts all masses at arbitrary distances. They feel this force of gravity. Now, Newton already knew there was something a bit funny about this. He didn't quite feel comfortable with this because he already realized, well, that means that somehow if there is something that happens arbitrarily far away, and if we have a sufficiently sensitive detector of gravity, we would immediately know about this. And this bothered people over the years, but people kind of came to terms with it because Newton's gravity was so good at explaining all of the laws of motion of planets around the sun and so on, until in 1915, a man who was one of whose talents was to stick out his tongue very far, Albert Einstein, came along and said, no, hold on. This can't work. Information cannot travel faster than the speed of light. We need to revise this Newtonian notion of gravity. And so Einstein replaced gravity with the theory of general relativity. And the theory of general relativity was based essentially on two main ideas. One is massive objects curve space and time around them. And Einstein's equations describe exactly how that space and time is curved by the presence of massive objects. You might think about it, as is done in this little picture here, as taking some sort of a sheet of lycra and putting a big bowling ball in the middle of it, right? And now you have this curvature in this lycra universe. And now the second part of Einstein's theory of general relativity describes how objects move in the now curved space-time. And the idea is objects really try to move on a straight line as much as they can, but the problem is they're trying to move in a straight line in the space which is no longer flat, which is curved. And so if you imagine having a funnel and you take a little ping pong ball and you kind of knock it, straight, and then you don't exert any forces on it, if you knock it straight at the right initial velocity, it'll just go in circles around the funnel. And yes, of course, because there is always some friction, eventually it loses energy and spirals into the funnel. But if you imagined somehow that it could perfectly slide on the edges of the funnel, it would just keep going around and around and around, just like this. And this is how, in Einstein's picture of gravity, planets move around the sun, or satellites move around the Earth, or the sun moves around in the entire galaxy, and so on. And there were, even in Einstein's times, already some tests of general relativity. One of them was Mercury's orbit. So there is something funny that happens to Mercury's orbit. And people had actually realized long before Einstein something funny was going on. So Mercury, remember, is the planet closest into the sun, and people have been measuring its trajectory for a long time. And the trajectory is a little bit eccentric. So it's not a perfect circle. It has a point of closest approach and a point of that's furthest away from the sun. And this orbit isn't quite a closed orbit. Every time Mercury goes around the sun, on every next iteration, and this is greatly exaggerated, the point of furthest approach moves a little bit. It shifts a little bit. It shifts by a small angle from orbit to orbit to orbit. So Mercury does something like this. And this shift was measured very precisely, and it turns out it doesn't quite match the prediction that you expect in classical Newtonian gravity. You can calculate the impact of all of the other planets, and it's not quite enough. And this is a tiny, tiny amount. It's a small fraction of a degree per century, but nonetheless, there's a very clear discrepancy there. And people have even postulated that maybe there's some other planet inside Mercury's orbit that hasn't been detected yet. People call it Vulcan. But nonetheless, nothing like that was observed. And then when Einstein did his calculations of general relativity, he didn't try to fit them to this particular observation. They actually came essentially from first principles. But it turned out that they perfectly explained this additional shift in the orbit of Mercury. But OK, that's a tiny effect. We don't really maybe care about it all that much in our practical lives. And we know that Newton's theory is approximately correct as long as things are moving slowly or as long as gravity is fairly weak. So here's the question for you. Can you think of any examples where general relativity is actually relevant even in your daily lives? GPS. Perfect answer. So the global positioning system has to, of course, very carefully account for the motion of the satellites. And if you don't include corrections due to general relativity, then after a few hours, you will realize that, well, when you type in the Aspen Center for Physics as your destination, if you're driving from somewhere a little bit further away, you won't end up in the right place anymore, right? So it's kind of important to have general relativity there. OK. So we need general relativity. There were other tests of general relativity that I won't have time to discuss now, but we now think it's correct. And one of the interesting predictions of general relativity, if we return back to this picture of massive objects creating something like a funnel in the space-time around them, is that if you have an object that's sufficiently massive and sufficiently dense, then this funnel becomes extremely steep. And the funnel can, in fact, become so steep that nothing, not even light, can escape. So if you have an object that's so dense that not even light can escape, what do we do with it? Well, we have our usual way of looking at things with electromagnetic waves, but how do you look for an object from which light cannot escape? Well, you can try, and it looks like this. That, ladies and gentlemen, is a black hole. Right? Not emitting any light, nothing to see. Sorry. Well, OK, if there was absolutely nothing to see, I probably wouldn't be talking to you today, because it would be a bit boring. Or we would be done now. It would be a very short talk. So let's talk a little bit more about the black holes, because maybe there is some hope after all. So here's again a picture of a black hole, this sort of imaginary funnel in space-time. This isn't really a black hole. The black hole is a tiny singularity. It's an extremely dense, infinitely dense point of matter, which comes out, as we'll discuss in a moment, when a very massive star collapses. And this is just a picture of the curvature of space-time. These lines aren't physical. There is nothing there that you can poke and touch. So it's just extremely dense collapsed matter, and the gravitational force is so strong that not even light can escape. And so how do we see this? How can you actually try to look for a black hole? Well, if you've seen the movie Interstellar, you may know of at least one way of seeing this. Right? So here's an image from Interstellar. And this is sort of this picture of what might happen if you have a light source behind the black hole. So the black hole acts as an extremely strong lens. Here you actually have a disk going around the black hole, what astronomers call an accretion disk. So it's a disk of matter that's gradually spiraling into the black hole. But you can see remarkably over here the back end of the disk, which would normally be obscured by the black hole, right? Here's your black hole, the disk is behind it. Normally you wouldn't be able to see it. But light feels this gravity, and just like objects that feel gravity go, for example, in circles or on ellipses, right? Remember planets going around the sun. Here, light is bent in just the same way. And so you actually see the back side of the disk that really should be behind the black hole being lensed in this crazy way, giving you such a apparently ridiculous image. How else might we look for black holes? Well, so turns out that we think there is a black hole in the center of our own galaxy, the Milky Way, that weighs in at about 4 million times the mass of the sun. Now, that particular black hole, the black hole in the center of our galaxy, doesn't actually have a big disk around it, and it's not particularly bright, and it's kind of hard to see on its own this way. But fortunately, it has stars around it. And so we can actually try to figure out that the black hole is there by looking at the stars going around the black hole. So here is an animation based on real data taken by our colleague Andrea Ghez and her group at the University of California, Los Angeles. And you see here, so this is the year. So this is, this animation takes something like 10 years. Sorry, I think I took a slightly out-of-date animation, so it ends in 2010. Of course, now there's data available up through 2015 through 2016. But the point you can see here is that these are the orbits of individual stars, and some of them are already closed orbits. So this is the S2 star, for example, that has actually completed a full orbit during the time of the observations. And you can see that these things are zooming around on very fast orbits, and you can calculate, just like you can calculate what the mass of the sun is by considering, for example, the orbital period of the Earth and the radius of the Earth's orbit. That's enough, using Newton's laws, to figure out what the mass of the sun ought to be. You can figure out what the mass of this thing over here, where this little white star is drawn, should be. And the mass of that thing turns out to be about 4 million solar masses. And yet, there's actually no source of light there, so we know it cannot be 4 million suns because that would be a very bright source. So the only conclusion is it must be a black hole. And in fact, just during this meeting that we are having here in Aspen, now we heard a very nice talk from one of our colleagues, Dimitrios Psaltis, about a proposal to specifically look for the event horizon of this black hole by using a spectacular telescope that would actually allow us to resolve things on much, much finer scales than what's shown in this picture. OK, so those were a couple of ways to look for black holes, right? We could look for matter being lensed by the black holes, or light being lensed by the black holes. We could look for stars going around the black holes. There is one more opportunity. And this opportunity is something that Einstein actually predicted almost immediately after he formulated the general theory of relativity. In 2015, he wrote down the equations of general relativity. In 2016, he already realized.
19.
I'm sorry?
19.
Sorry, did I say 20? Thank you very much. Thank you for the correction. Somebody is listening. Wrong century. 1915, of course, he wrote down the equations of general relativity. And by 1916, he already realized that these equations naturally predicted that just like in classical electricity and magnetism, there are electromagnetic waves, things that we see as light, there is something in general relativity that describes the propagation of ripples in the fabric of space-time itself. And those are gravitational waves. So gravitational waves are perturbations in space-time that propagate at the speed of light. They move out like ripples on a pond and are generated by typically very rapidly moving and accelerating dense, massive objects. They actually generate quite a bit of energy, but by the time they typically get to us, they are very weak. And what they do is they stretch and squeeze space. So if you've ever wanted to appear a little bit slimmer and a little bit taller, all you have to do is wait for the gravitational wave to pass through, and you look far more handsome. Now, two problems with that. One is gravitational waves, they're waves, so they oscillate, which means that in one half cycle, you look like this, and the next half cycle, you look like this. So maybe you don't look quite as good. The other problem is they kind of don't stretch and squeeze you by very much. If you want to impress your partner, you'd better hope that your partner has very good eyesight, because the typical stretching and squeezing for the kinds of things we're looking for is 1 part in 10 to the 21st power. So 1 divided by 10 with 20 more zeros written on the end. But in principle, we could hope to look for these things. And this is the idea of gravitational waves. So now we don't have a telescope here. We have a detector. And this is the LIGO detector, Laser Interferometer Gravitational Wave Observatory, that Vicky has mentioned. And so we can try to detect ripples in space-time. Now, the way it basically works is you take a laser beam, you pass it through a mirror that splits the beam going down the 2 detector arms, and you hang mirrors on pendula at the ends of the 2 arms. And when a gravitational wave passes through, it moves those pendula, therefore moves the mirrors, so one arm gets a little longer, one arm gets a bit shorter. Then in the next half a cycle, this arm gets a little shorter, this arm gets a little longer, except now we're talking about 4-kilometer long arms, not my arms. That's in order to exaggerate the signature of the gravitational waves. And from this alternation in the length of the 2 arms, that causes the light coming back from the 2 arms to have a slight difference in phase. And you can try to measure that little difference in phase. And that little difference in phase tells you that there was a gravitational wave source that caused the arms to change in length relative to each other. Therefore, hopefully, it means that a gravitational wave has passed through the detector. Now, it's a very difficult project because even with 4-kilometer long arms, here's one of the LIGO detectors. There are actually a couple of them in the US, one in Louisiana, one in Washington State. This is the one in Hanford, Washington. There are also some international detectors that aren't quite operating yet, but will be coming online shortly, one in Italy, one in Japan, eventually one in India. But this is one of the currently working and operating detectors. In fact, actually, right at this moment, it should be operating because it's in the middle of an engineering run. But with 4-kilometer long arms, you're still trying to measure mirrors shifting by 1/1000th of the size of an atomic nucleus. This is the kind of precision you're looking for. You're trying to measure effectively the relative accuracy of the measurement of the length of the two arms is about the same as trying to measure the distance to the nearest star, Alpha Centauri, to the thickness of a human hair. Imagine trying to do that. So, of course, as you might expect, a proposition like this requires a big team. And in fact, we are very fortunate to have a big team. This is the LIGO Scientific Collaboration. Here's my university over here, University of Birmingham in the UK, formerly in Europe, not as of 2 weeks ago, unfortunately. And as you can see, there are many, many other institutions here. Here's Vicky's favorite, Northwestern. So it's really a global effort. I think Antarctica is unfortunately not represented yet, but we'll work on that. And there's a fantastic team of scientists who've been building these detectors and figuring out how to analyze the data for many years. And there are many challenges involved. There are many sources of noise. I won't go into the details. This is just sort of telling you that at different frequencies at which you might be looking for gravitational waves, you have different noise sources. At low frequencies, seismic noise, the ground shaking basically. At high frequencies, what's called shot noise, the fact that you actually care about the fact that you have individual photons with which you're trying to measure the position of the mirror, and you're trying to count those photons. That's what it means to try to measure the distance. And you have random fluctuations because of that, and some less expected noise sources. So this particular detector, the Hanford one, is located in the middle of nowhere, really in eastern Washington state. And once in a while, there's a ranger patrol car that goes by to see if things are okay on this reservation where it's located. I'm not sure how much this ranger is able to spot if he can't spot 4-kilometer long arms, but there you go. It happens. So this is one of the unanticipated noise sources. But nonetheless, you can see the experiment was that it was built even with crazy rangers in mind. Nonetheless, after many, many years of effort by a very large number of people, late last year, in fact, in September 14th of 2015, I'm careful now about which century I'm in, September 14th of 2015, our detectors observed something that looked very much like a gravitational wave. And of course, we were very careful, so we took 5 months to very carefully analyze the data, vet it, look at it in every possible way, and eventually we submitted a paper to a journal describing the first observation of gravitational waves from the merger of two black holes spiraling together. This is, as I said, work by actually slightly more than 1,000 people, so I can't even give credit to all of the people here, but when I was talking about this to one of my colleagues who works at the Large Hadron Collider, a particle physicist, he told me, you aren't a real collaboration unless you have in your author list somebody starting with every letter of the alphabet. So I checked whether we were a real collaboration or not. And here's just the tail end of the author list. That spans, the author list here spans something like 3 pages. And I looked at this, and I noticed that here's Wu and here's Yablon. There is nobody that starts with an X. So the LIGO collaboration is still looking for a few good women and men to join, especially if your name starts with an X or if you're willing to go through a name change. Please come talk to me afterwards. We're looking for you. Now, this is what the signal actually looks like. So this gray business over here is the data, and the curves you see on top are our gravitational waves. These gravitational waves that we see in this case, as I said, from the spiraling together of two black holes. But gravitational waves, although we can draw pretty pictures of them like this, they really shouldn't be seen. They should be heard. So they're just the opposite of children in that sense. And we can actually, so here's our first attempt at singing. Let's try to think about what a gravitational wave might sound like. Right? So you have two objects, and they're coming closer and closer together, and they are sending out ripples in space. Now, first question, what do you think is going to happen to the frequency or the pitch of these ripples as the gravitational waves get closer together? It's going up, right? Because as you get closer and closer together, you go around faster and faster. Like, and a year on Jupiter is much longer than a year on Earth, right? Because Jupiter is further away from the sun, and so an orbit takes a lot longer. Okay, so as you come in together, the pitch goes up. The second thing that should happen is the amplitude should change, right? And again, as you get closer and closer together, there's more interaction, and you might expect that the signal gets stronger. So the amplitude goes up. So we need to come up with something where the frequency and the amplitude goes up. So let's try to do this. This, by the way, is the test for getting into the LIGO collaboration, whether you can do this. Let's write it together. Come on, we can do this. Let's do a chirp. Fantastic. Okay, all of you are now welcome as LIGO members. And we've done at least a little bit of singing. This is the singing of black holes. Actually, the remarkable thing is we got the frequencies mostly right, and even the evolution timescales mostly right. We just ever so slightly increased the amplitude. If we're talking about fractional changes of 1 part in 10 to the 21st, 1 part in 10 to the 20 zeros behind it, unless you're a really good sonar operator, chances are not very good of being able to detect that. One of my students had actually tried to generate the sounds of gravitational waves, so we can actually hear how close we are. So let's try to listen to this. Yep, definitely a chirp. Amplitude is going up, frequency is going up. This was a neutron star falling into a massive black hole. This is not a real observed event. This is our simulation. Here are... Oh, this really is, so we haven't sped up the time here. So really, when we're talking about how long these signals spend in the band of the detectors, it really is between a fraction of a second and a few seconds. Maybe as detectors get more sensitive, some of the lower mass signals will go to a few minutes. But really, we're only catching the very tail end, the last few seconds or at most few minutes in the lives of this pair of black holes. Now, okay, just as an example, let's look at two more massive black holes. Here's a black hole weighing in 14 solar masses and 50 solar masses, and they're spiraling in together. In general, it sounds a bit different. The rate at which the frequency is changing is a bit different, but the overall behavior is still the same. It's still a chirp. So now we can finally make sense of this cartoon from the New Yorker. By the way, I really think that the field has really made it when you get a cartoon in the New Yorker, which is kind of an inside joke. It shows that you've really reached public consciousness, right? So here are two birds. And OK, this is hard to read, so I just wrote it down underneath. Was it you I heard just now, or were the two black holes colliding? So I guess I heard a chirp. So now you get the joke, right? OK, so we talked a little bit about gravitational waves. Now I want to say a few words about how do we actually make these things, right? I mean, OK, I told you that one of the ways to make gravitational waves is to have two black holes spiraling in together, emitting gravitational waves, therefore losing energy in the process, and gradually falling into each other. And that's what we were listening to, right? But how do you actually get two black holes there? That's actually one of the very interesting questions, and many of the people at this meeting in Aspen, including Vicky and Fred and many others in this room, have been thinking for many years about how you might do this. So I'll try a very simple picture of this. Now, the first place to start is to realize that our sun is kind of unusual. Our sun is very lonely. It's just sitting there all by itself with a few planets going around it, but no companion. This if you think that Star Wars is fiction, this is actually much more realistic, right? The notion of having two stars is par for the course. In fact, I hope that nobody objects too much to polygamy, because in fact, many stars like to be not just in pairs or binaries, but sometimes in triples and quadruples and other kinds of funky relationships. But this is perfectly normal, so stars feel lonely and like to be in pairs. And so we have our two happy stars. Let's call them Stella and Estelle, sitting there dancing around each other, right? I'm not very good at animations, but really those two stars aren't just going to be able to sit there, right? If I just put them in place and they weren't moving, they would immediately fall into each other, right? They're instead dancing. They're going through a nice little tango, going around each other like this, right? Just like the Earth going around the sun, except now they are much more similar in mass. But these aren't normal stars, right? These are rock stars. They're cool. So they're rock stars because the stars that I'm particularly interested in aren't the ones like our sun. Our sun is kind of a boring star. It's been around for 5 billion years already. It'll be around for another 5 billion years before it really does anything interesting. It's gradually producing a bit of light by fusing some hydrogen to make helium, and it's doing this at a pretty slow rate. I mean, 1 cubic meter of the sun produces less energy than one of those light bulbs, right? So it's pretty pathetic as far as stars go. Now, there are other stars which really are the rock stars of the stellar world, right? What do rock stars do? They burn bright and die young, right? That's so if you take a star that's a lot more massive than the sun, let's say 50 or maybe even 100 times more massive than the sun, it's going to burn through all of that hydrogen, right? 50 times more hydrogen. When I say burn, I mean fuse the hydrogen to make helium. It's going to go through all of that in only a few million years, as opposed to 10 billion years for the sun. So it's very energetic, and it's so energetic that it's, during its rock star performance, it's spewing out confetti like crazy. Okay, it's not quite confetti. In this case, it's actually stellar winds. So the star is, our sun also has some winds, right? Our sun is spewing a bit of material out into space, but it's really a tiny amount, almost negligible. Whereas these kinds of stars, some of them might, depending on the state of their evolution, might lose something like 1,000th of the mass of the sun in 1 year. They're just really happy and willing to share. Now, they also do some other crazy things. One of the things is that as they get a little bit older, this sometimes happens to rock stars, their fame gets to them a bit and they start expanding. And when they expand, before they were dancing sort of at a, some genteel way at some distance from each other, but as they start expanding, they get closer and closer together. And as they get closer and closer together, well, what happens is, of course, that initially you form tides on them, right? Just like the moon going around the Earth, forming tides where the oceans are a little bit closer to the moon on one side, a little bit further on the other side. And so you have a bit of an extra force acting on the Earth's oceans, which causes some deformations in those oceans. But eventually, what can happen is if one of the stars starts getting too big and they get too close together, those tides become gigantic. Unlike tides of a few meters on the surface of the Earth, they can be tides that are hundreds of thousands of kilometers in size. And at some point, the stars actually start getting into contact. They touch each other, and so they start, in fact, transmitting some mass from one to the other. So it's not just a silly picture like this. There are actually observations. Well, in this case, it's sort of a mixture of an observation and some artwork of two stars, one of them which has expanded, and as you can see in this bit of artwork here, is transferring some mass to its companion. Now, we won't go into too much detail of how the stars transfer mass to each other because, after all, we don't want to get too much into the private lives of rock stars. So at some point when they get too close and personal, we'll call it a common envelope. That's what the astronomers call it. And we'll happily hide whatever is going on between those two stars underneath this common envelope, which is mostly to say that this is one of the big unanswered puzzles in astrophysics. We don't really fully understand how this process of very rapid mass transfer between the two stars works. Now, there's one more thing that can happen, of course, to stars. So here's our star happily sitting along, and remember, it's aging. It's now converted most of its hydrogen to helium, and eventually it converts its helium into carbon and nitrogen and oxygen, and this goes on until iron. And during all of this time, the star is releasing energy. Because this is the idea behind nuclear fusion, right? If you take two light atoms together and make a heavier atom, the process is exothermic, meaning it releases energy. And this release of energy is very important because remember, the star is big, right? It's very massive. It feels a lot of self-gravity, right? You know, the outer parts of the star are being pulled in very strongly. And something has to balance this gravity to prevent the star from just collapsing on itself. And it's this release of energy, this thermal energy that's produced as the star is undergoing fusion, that balances the inward pressure of gravity. But there comes a time when the star runs out of fuel. And when it runs out of fuel, if it's massive enough, it's very hard to now prevent the star from collapsing. So stars like our sun, when they run out of fuel, they become white dwarfs, which means that they're supported by the quantum mechanical degeneracy pressure of electrons. And slightly more massive stars become neutron stars, which are supported by the Fermi degeneracy pressure of neutrons. And by the way, these are already very compact objects. A white dwarf with the mass of our sun is only going to be about the size of the Earth. A neutron star with a mass a bit larger than the mass of our sun is going to be only about 10 or 15 kilometers in radius. But if something is even more massive than a neutron star, if the initial mass of the star was, give or take, more than 20 times the mass of the sun, when it runs out of thermal energy, when it is no longer able to undergo nuclear fusion, it may undergo a supernova, which is this lovely explosion, and then collapse into a black hole. Because nothing can fight the gravitational pressure that's causing the star to collapse. And so now we've talked through most of the difficult phases of the evolution of a binary. You start out with two stars. Maybe there's a bit of mass transfer. There's a supernova that maybe causes one of the objects to change its velocity because there's a possibility that it shoots off a bit of extra mass one way rather than another. And if more mass goes one way, it's a bit like a rocket effect. So a rocket shoots out gas one way, and then the rocket flies, is accelerated the other way. So the same thing can happen to stars. Then there is this, with lots of question marks, this common envelope phase that we won't talk about. It's a bit of a dirty word. And some mass loss through these winds, this confetti that I talked about earlier. Maybe the second star goes supernova. And finally, surprisingly, the part we actually understand best theoretically is the last part where some gravitational waves are emitted and the two objects merge together. And this is my little cartoon, but it's actually not that different from some calculations that our colleagues have done. So for example, I'm not going to talk through this in any detail, but this is from a recent paper published in Nature by one of our collaborators. And you can see it kind of goes through the same phases, but now doing a much more careful calculation of this. Now, there are a couple of other channels for making these kinds of stars that I won't focus on, so let me skip over the next couple of slides. And let me instead go to dinosaurs, because I promised you I would show you some dinosaurs. And given that I only have a few minutes left, dinosaurs are important. So remember we said that it's not just about detecting gravitational waves. We want to do something with them. We want to learn astrophysics from these observations. Well, how do we do that? Because, as we said, we're only seeing the last few seconds or the last few minutes in the lives of these black holes. What I want to know is, remember all those question marks that I showed you? I want to understand more about those question marks. I want to figure out how those stars evolve, how those stars and binaries evolve. How do I do that if all I have are the last few seconds in the lives of the stars? Well, maybe we can take a little hint from the paleontologist, right? Imagine a paleontologist sees the skull of a dinosaur like this. Well, if she's a good paleontologist, she probably can figure out, just from the skull, never of course having seen a living dinosaur, what the dinosaur looked like, what it ate, how it behaved. She can reconstruct from that skull this picture of a living, breathing, walking, talking, well, hopefully not talking dinosaur. Now, we do have some complications because we don't actually get this nice skull from our gravitational-wave observations, nothing we can hold in our hand. We do have this signature of the remnants of massive stars, namely the two merging black holes, but we don't really have very accurate measurements. It's hard enough to detect the gravitational waves at all. It took decades to get to this point. The data is noisy, and we can only extract limited information from it. And this is actually one of the things that some of us have been working quite hard on, how to extract all the available information, but it's still a difficult problem. So instead of a skull like this, all we see is some shady outline of a skull over here. But nonetheless, it's better than nothing because it gives us a whole different handle that we simply couldn't have using just electromagnetic observations. Because we now know something, at least, about those remnants of the massive stars. We know something about the population of those remnants, and that allows us to go back and try to answer some of these big question marks. And that's what many of us are actually here this week to think about, how you might try to go about doing this. And I think I'm probably at the end of my time, so let me just show you one final movie while we're going to take questions. Thank you. The movie isn't working. Please.
Yes. So I was wondering what happens with time. Well, let me go back. With your wave, I would assume that the amplitude of the wave implies the position of the masses. As the masses are aligned with you, maybe it's at high amplitude. As they are square with you, it's at the low amplitude. And it would almost infer then at the rate you're seeing the wave that they're going around each other quite fast.
Absolutely.
Incredibly fast.
Absolutely.
And that would, and if time weren't changed, how fast would those masses be going around? But is there not a distortion of time as well? And what does that mean between the rates that they're going under their own massive influence versus what you see in a less gravitational rate?
So you're absolutely right. So when I showed you these waves and when I played them for you, right, when we made these sounds, right, they're in the audible band. LIGO is sensitive to things which are in the audible band, basically meaning it's sensitive to signals which have frequencies between about 10 hertz and 1,000 hertz, which means 10 to 1,000 cycles per second, right? So that means that the black holes are going around each other, turns out, at half the rate. So the gravitational wave frequency is twice the orbital frequency. But it still means that you have these massive objects going around each other many, many times per second. So they are moving incredibly quickly. In fact, they're moving in the last few moments before merger at a significant fraction of the speed of light. So this is hugely slowed down over here. But you see here these two black holes that are just about to merge. And at this point, they're in fact moving at something like half of the speed of light. So you're absolutely right. It's an incredibly strong and rapidly evolving dynamical interaction. I don't remember who was next, but please.
What happens when, if at the center of galaxies there are massive black holes? What happens if two of them, with all the stars around them, collide?
So the question was, what happens when two galaxies hosting two massive black holes collide? And we know this happens. We know that galaxies do merge. We have observations of galaxies merging. And we think that what happens is that the two massive black holes will sink quite quickly to the center of the newly formed galaxy and will eventually merge with each other as well. Now, those signals, they will also emit gravitational waves, even stronger gravitational waves, but at much lower frequencies. The frequency goes inversely proportional to the mass. So higher masses means lower frequencies. That means detectors based on Earth cannot see such signals because we have too much ground shaking and so on at frequencies that are at thousands of a hertz, for example, or 1 cycle per hour, let's say. But we can try to look for these things with other kinds of detectors. And there are, in fact, 2 ideas underway for how to look for them. One is to put a detector very much like LIGO, an interferometer, but in space, where the laser light is now being sent between a group of 3 satellites. So instead of this beam splitter and the 2 mirrors at the end of the arms, you actually have 3 satellites, and they're exchanging laser pulses between them, and you try to measure the distances between the satellites and the change in those distances due to gravitational waves passing through. And this is an experiment called LISA, and it's still in the planning stages, but just very recently, the LISA Pathfinder, which was a test of some of the LISA technology, was very successfully launched and showed the technology is ready. So hopefully, in the next 10, 15 years, we will have LISA being launched into space, and that will allow us to probe such systems. Another opportunity, actually, is something that nature has given us for free. There are these objects called neutron stars that I mentioned earlier, and some of them are very rapidly spinning. And those very rapidly spinning neutron stars, if they are emitting light because, or radio waves in this case, because there's a bit of a misalignment between their magnetic fields and their axis of rotation, we call them pulsars. They aren't actually pulsing, they're always emitting light, but imagine here's a neutron star, I'm shining light radio waves at you. Now I turn, and now I'm shining radio waves at you again, right? And I turn and shine radio waves at you again. So to you it looks like I'm pulsing, but I'm actually sort of a cosmic lighthouse spinning around. Now if I'm this cosmic lighthouse spinning around, and I'm constantly emitting these radio waves are propagating through the fabric of space-time towards you. And now imagine somewhere far, far away, there's a merger of 2 very massive black holes, 1 billion times the mass of the sun. Now, there are gravitational waves coming out because of that merger of 2 massive black holes, and the radio photons from the pulsar are kind of surfing on the gravitational waves. And because they're surfing on the gravitational waves, they don't arrive exactly when you expect. Sometimes they arrive a little bit too early, sometimes they arrive a little bit too late. We can predict pulsars for some of the very stable pulsars. We can predict exactly when the photons will arrive to an accuracy of 100 nanoseconds going forward by years, right? And so we can see these little tiny deviations in the arrival time and say, those are possible signatures of gravitational waves. And that's actually one of the other experiments that's going on, because nature has provided us with a free gravitational wave detector.
What is the length of the LISA arms, and that turn that back into time?
Yeah, so LISA arms are about depending on the design, between 1 million kilometers and 5 million kilometers long. So that's why they're able to look for much lower frequency gravitational waves. Indeed. Sorry.
I was going to actually ask if the LISA was going to be put into like Lagrangian points, which would be one thing, and then the other thing did you have any corroboration through anything like a synchrotron radiation that you could sync up with the gravitational waves? Was there anything like that was observed?
So LISA is probably not going to go into Lagrange point. It's going to be, there are actually some discussions about where is the best place to put LISA. That's still not fully decided. It depends a bit on how much money there is for it. But it may actually be something like following roughly in the Earth's orbit around the sun, but maybe as much as 20 degrees behind the Earth. You actually don't want it to be too close to the Earth, because you don't want the Earth to basically perturb the LISA constellation. As far as electromagnetic counterparts, there is one claim of possible gamma ray bursts that were associated a very weak gamma ray burst signal that may have been associated with the gravitational wave emission. There are other groups that looked in a similar part of the electromagnetic spectrum and have not detected anything, so there is quite a bit of debate about this. But given that these are two black holes, we wouldn't necessarily expect to have a strong electromagnetic signal, because to have an electromagnetic signal, you need matter. And if you just have two black holes merging together, there may be very little or no matter around them, so you wouldn't necessarily expect such a signature. If you had, for example, a merger of two neutron stars, which is another possible gravitational wave source, then we would expect quite likely a very strong electromagnetic signal that we could match up with it. In fact, Vicky has recently won a prize in part for demonstrating that it's very probable that one of the kinds of electromagnetic signals we already have seen, called short gamma ray bursts, is likely associated with the merger of two neutron stars. Yes, please.
A few years ago, the microwave background, some of the physicists thought they detected gravitational waves. Turned out to be dust. But what was it that they thought was creating? This was before black holes.
Absolutely. So that was gravitational waves in the very early universe that were imprinting themselves in the cosmic microwave background. The cosmic microwave background is light that's coming to us from the first 300,000 years in the life of the universe. And the idea is that if you have initially perturbations in the distribution of matter, and we think there must be such perturbations because we see that today in the universe that we see around us, the universe is not homogeneous. It's not isotropic, right? You and I are here. We are fairly dense. If we look, out there, the things are much less dense. If we look far beyond our galaxy, things are extremely empty, right? So clearly the universe isn't uniform. But we think it started out as some relatively uniform hot dense soup. And so there must have been some initial perturbations, which later on, of course, the slightly more dense regions exerted a slightly bigger gravitational pull, which brought even more matter there. And those little overdensities grew and made even larger overdensities. And the gravitational waves we're talking about here are the gravitational waves that are associated with these very early perturbations in the early universe. By the way, I should say I'm very happy to take more questions, but I realize it's getting close to 6:30, and some of you probably want to go home. So if you want to go home, I won't be offended if you leave at this point, but I'm happy to keep talking. Yes, please.
So as far as I understand it, the black hole has the same mass as supermassive star that created it. So if that's the case, what's different about the black hole that makes it so that its gravitational waves can be detected, but the supermassive stars can't?
So you're absolutely right that the mass, it's not quite going to be the same mass, but it's very close to the mass of the star that formed it. Some of the mass may be lost in the process of the supernova, in the process of forming the black hole. But the star is, so in order to create gravitational waves, it's not enough to just have one black hole, right? If you just have one black hole sitting there doing nothing, it's not going to create gravitational waves. You need something which is moving and, in fact, accelerating. And ideally, if you want to have a strong gravitational wave signal, you want something that is moving very quickly. And for that, you need to have two objects that are very close to each other. Now, if you put a massive star very close to another object, the massive star is going to get shredded, right? It's going to be like the picture that I showed, where the star gets distorted because its friend is pulling it a little bit too hard. And so massive stars could, in principle, generate gravitational waves, but they would be at extremely low frequencies, and also their amplitudes would be very low because the stars are still quite far apart in order to avoid getting shredded by their companion they're dancing around with. Whereas black holes can get really, really close together. And that's why the frequencies get higher, the velocities get higher, and the amplitude of the gravitational wave signal gets much, much louder. Please.
Why can you detect a difference in the gravity around the colliding black holes and not detect the light?
So if you have two black holes, the black holes, so you have to think about what's emitting the light, right? So in order to emit any kind of light, any kind of electromagnetic radiation, the process is always essentially the same. What you have, it's just like a radio antenna, right? You take an electron and you shake it around, and as the electron is accelerating, it's emitting what's called Bremsstrahlung radiation, but basically it's emitting radiation because you're accelerating an electric charge. Now, to have an electron, you need to have some kind of matter, right? You need to have gas, you need to have plasma, you need to have something there. If you just have two black holes, the black holes are singularities. They are bits, they do have mass, but that mass is contained in a volume that's infinitesimally small, so they're infinitesimally dense. The space is curved hugely around them. In my example of a little Lycra sheet, think of something that has created a funnel so deep that it tore all the way through this Lycra sheet. And so that matter which is inside the black hole has no way of getting out, has no way of sending light out. The walls of this funnel are too steep. This is what's called an event horizon, so nothing can get outside. You can fall inside the event horizon just fine, except you won't be able to tell me standing outside what you felt or what you saw once you've fallen in, because there is no way you can send a signal outwards. And so these two black holes, when they merge, what they actually do is they create a common event horizon. They combine their two event horizons and immediately form a single larger event horizon. You'll be able to see this in a moment over here. So those two black spheres are the two event horizons. Eventually they'll form a single event horizon that encompasses both of them. And so that matter doesn't get out. The light doesn't get out. The only way you could create an electromagnetic signature is if, so there's your common event horizon, single black hole, is that there was some other matter out here that didn't fall into the black holes, that was somehow impacted by this merger of two black holes, and then that matter could radiate away. So if that were to happen, then absolutely you could see such a signal. Please.
The data you have now, is there any way you could find a graviton, the individual particle?
No. Unfortunately, we're... The sensitivities that would be needed to look for individual gravitons are far, far beyond what we're capable of doing with our detectors right now. We're still very much in the wave regime rather than the particle regime as far as the gravitational waves go. Yes, please.
How did you overcome the perturbations in the gravity wave on your measuring devices? So as the wave came through, your measuring device changed too. So how does your measuring device got longer and shorter? How do you overcome that?
So that's actually a really good question. And this comes to one of the difficulties of general relativity, which is that there is no notion of absolute space and absolute time. And in fact, I talked about the mirrors moving in the ends of the two arms. I could have talked about, for example, mirrors staying put and the speed of light in the two arms changing. Right. It's what physicists call a choice of a gauge. Think of it as kind of a choice of a coordinate system, right? I can choose to measure the same quantity in different coordinates, right? You can measure something with an inch ruler. I can measure something with a centimeter ruler. We'll get supposedly different answers, but of course it's actually the same. You'll say something as 10 inches, and I'll say it's 25 centimeters, but it's really the same object, right? So it's kind of a deeper version of the same issue. But so there is no simple way to unambiguously say what actually does change and what doesn't. But the point is that, of course, as with any physical theory, observational results we ought to be able to predict in a self-consistent way, independently of what kind of a gauge or what kind of a coordinate system we choose. And people have analyzed this problem in multiple different choices of gauge, and the observational result predicted is always the same, that there really is a signal that we ought to be able to detect here. I think there was a hand in the back for a while.
Yeah, a couple of questions. Could you explain, since it's the case that I've heard that these collapsing black holes emitted more energy than has been emitted by all the stars in the history of the universe, can you explain, or corroborate that or correct that, and explain what it would be like if we were actually in the same galaxy? And do we know where it came from? And also, how often are these believed to occur, the colliding black holes? And And let's see, the last question is...
Well, maybe I'll try to answer the ones you've asked so far, because otherwise I'm afraid I'll forget all of them. Okay, so the first question was, how much energy do these things actually emit? So the amount of energy that was emitted from the first event that LIGO has observed, and now at this point LIGO has observed actually almost 3 events. We have 2 confident detections and 1 very likely candidate that's not quite loud enough for us to call it confident, but I'm personally fairly convinced it's a real event. So the first one of these emitted about 3 solar masses worth of energy. And when I say solar masses worth of energy, what I mean is that if you use Einstein's formula to say that energy equals mass times speed of light squared, E equals mc squared, then it's the equivalent of converting the full mass of the sun into energy and doing that 3 times over. And by the way, just for comparison, during its entire evolutionary history, our sun will only manage to convert about 1/1000th of its mass into energy, because that's all that you can get out of merging hydrogen to make helium. Now, that's not, those 3 solar masses worth of energy is not larger than all of the stars in the entire universe have emitted over the age of the universe. However, what I think you were probably referring to is the fact that the instantaneous luminosity, the rate of energy generated per unit time, was indeed greater for the signal than for all the stars in the universe at that moment put together. And that's because those 3 solar masses worth of energy were emitted over a time that was less than 1 second, right? Whereas stars like our sun, right, as we said, they very gradually burn this energy over billions of years.
What if we were in the same galaxy?
Even if you were in the same galaxy, probably not very much would actually happen to you. You'd have to be quite close for the gravitational waves to really cause you noticeable problems. If this really happened in your backyard, if you were, for example, somehow on a planet in a planetary system around, let's say, not likely around a black hole, but around a neutron star, and we actually do know of planetary systems around neutron stars, and the neutron star binary merged, yes, you would be in quite a bit of trouble. I wouldn't envy you. But probably you wouldn't survive being even that close to a single neutron star, forget about a binary neutron star, so not too much to worry about. In terms of the rates at which these things happen, we think that in a galaxy like ours, there is a merger of 2 black holes probably happening between once a million years to maybe once every 10 million years. On the upper end, maybe 10 times per million years. Actually, probably once per 10 million years is too low. Let's say between once per million years and 10 times per million years. Another way of saying this is that, in the first 4 months of operation, the advanced LIGO instruments have seen, let's say, 3 events. So it's about 1 event per month, and the detectors will only get more sensitive. So as our detectors are upgraded, we're going to expect that towards the end of the decade, we may be seeing these things as often as once per day.
Do we know where it came from?
Do we know where these came from? These came from, so the 3 events that we saw came from about 1.5 to 3 billion light years away. Where exactly in the sky, we don't know that very well. It's very hard to localize gravitational waves in the sky. It's sort of a region about, yay big on the sky that we're talking about. So it's not quite like electromagnetic observations, which can really pinpoint things to a tiny fraction of a degree.
So Vicky said that this was maybe the greatest discovery of the century, but what exactly does it imply?
So there are a few things we already learned from this. One of the things, of course, is a confirmation of Einstein's general theory of relativity. Another is our ability to test gravity in a very strong gravity regime, dynamical regime. So already we have a much, much more stringent test on gravity on very rapidly evolving timescales and in a very strong gravity regime than we could ever have before. And so we have a much better confirmation of general relativity than was previously available. And of course, this is opening up a new way of looking at the universe. Have been through some positive. No, I think here there was no sound associated with this movie. Yes, please.
Is there any theory on the demise of a black hole? Obviously, everything has a lifespan. Any ideas?
So
Maximum entropy, repulsive gravity. You know that there's spin, charge, and mass. Any one fluctuation that could cause a phase transition.
So there is something called Hawking radiation, which is a quantum mechanical effect.
No, that's too.
So that can cause a.
Too small. A black hole has to be too.
That's right. That's right. So a very small black hole can actually evaporate through Hawking radiation. Astrophysical black holes, things that of the size that we're talking about, stellar sized or many times the stellar size. No, they only get bigger. They don't get smaller. These kinds of black holes can only grow, and quantum mechanical effects are essentially irrelevant because they're growing by eating up mass many orders of magnitude faster than they can lose energy through Hawking radiation. So I suppose so. I think that's a philosophical point, so I'm not sure I can really comment on it, but if you choose to think of it that way, yes. So is this a good point to end?
Thank you. Thank you.
Thanks.
Thank you all for coming.
Thank you very much.